Hello, everybody. This is Dr. Frankie. If you're listening to this, the chances are I'm probably in Santiago, Chile right now, doing some research and presenting some of our earthquake findings at a big conference that happens every 6 years. I want to welcome you to the Elementary Soil Mechanics class, CEEN 341. I'm excited to get the chance to meet each one of you. And I know this is going to be a fun class. This is a class where I see a lot of students come in. They don't really have a lot of interest or any particular fancy with soil mechanics or geotechnical engineering. But by the end of the class, they're really excited. They seem to appreciate it a lot more, and we tend to have several students. There's probably on average between 5 or 10% of you listening to this right now that will eventually change your direction and want to pursue a career in geotechnical engineering, in large part because of this class. So I'm excited to have you. A couple of things before I get into today's lecture. These are things that I usually go over on the first day of class, so I'd like to review them with you right now. I'm going to pull up a whiteboard here, and we're going to review a couple of things. So very first thing, I want to talk a little bit about the syllabus. It's really important that you read the syllabus, that you read it in detail, because there's a lot of important things in there that could affect your grade and your performance in the class. A couple of things I want to just focus on here. First of all, we're going to do 2 homework assignments per week. After every lecture that we have, there's a new homework assignment given, but we only had homework in once per week. So since we have 2 lectures every week, there's 2 assignments every week, but you're going to hand in 2 assignments every Tuesday evening by 5 p.m. There's a slot outside of my office door. My office is room 368, P as in Polo, in the Clyde building up in the civil engineering suite. Just come up and submit your homework in that box by 5 p.m. every Tuesday, and my graders will take care of it and have it returned to you in the outbox or the folders right there below the box on that little shelf there, usually by the end of that same week. So just plan on doing 2 homework assignments every single week. Now I want to point out that there were a couple instances in our department last semester of some dishonest students taking other students' homework from homework piles and not returning them and just copying them and handing it in as their own work. This is not going to be tolerated, and if we start having a problem with that again in our class this semester, we're going to change the homework procedures and have you guys hand homework in a locked and secure box. I've never had this problem before in the years I've been teaching until last semester, and so hopefully it's a one-time thing and we won't have to deal with it again. If you are aware of any problems like that happening or know of somebody who's committing these practices, please let me know and we'll take care of it. We, in this class, we also have a weekly soils lab that you're going to participate in. As part of that lab, most of the labs are going to have a weekly lab report that you're going to participate in. So every week when you go to lab, you're going to do an experiment, you're going to collect your data, then you're going to summarize the data in a lab report and submit that the following week at your lab. It will be graded and assessed, and you'll receive a score for that. The lab is a substantial portion of your grade, so I encourage you to take it seriously and participate right from day one in your labs. But with that being said, I do want to emphasize, please, that there is no labs this week, the first week of school. That instead, what we're doing is we start the labs the second week of school. But this first week you have off from lab, so don't worry about going to your lab section this week. Start going the week of January 17th. When we're talking about homework and lab reports, if I understand life happens, things happen, and sometimes you need a break and sometimes you need to hand stuff in late. So I do allow 1 late lab report and 1 late homework pair, not assignment, but pair, to be submitted without penalty. Otherwise, when you submit homework or a lab report late, it's a 10% per business day policy. So every business day that it's late, I will deduct 10% from it, and that's fine. So if you need to submit something late, just go get it stamped by the secretaries, and they'll put a timestamp on it and then submit it in my box. Just indicate that it's late, and we'll take care of it. Another thing we want to talk about, of course, is the writing group. One of the important things about this class is improving your technical writing. Now, this is not a technical writing class, but this is a class where you're going to apply and practice your technical writing. So my job is not necessarily to teach you technical writing skills, but it's to critique and help you sharpen and improve your current technical writing skills. One of the best ways I found to do this is to receive peer criticism or peer review of your writing. To encourage this, we formed what we call writing group. Writing group is just a group of your peers that gets together once a week and brings 1 to 2 pages of technical writing, usually double spaced, and shares it with the rest of the members of the group. And so everybody gets their own copy of your writing, and then the group will spend 5, 6, 7 minutes reading, critiquing your writing, and then giving you a very what's the word I'm looking for? Give you the feedback and the criticism, and then hopefully you'll take that feedback and criticism and you'll improve upon it, and the next week your writing will be a little bit better. And so it's something that you do every single week. It's not mandatory or required in this class. I want to emphasize that. But I do want to encourage you and incentivize your participation. So to do that, what I've done is I've set up a program where if you attend at least 6 weeks of writing group and participate, I'll give you a 1% bump in your final grade. If you attend and participate in at least 12 weeks of writing group, I'm going to give you a 3% bump in your final grade. That's a full half grade improvement in your final grade. And so that can make a big difference. So I'll give you the dates and times for writing group. Those will start next week as well with the labs. So we need to find a room where you guys can meet. Usually writing group meets are between 5 and 6 p.m. once a week. So it's outside of the regular school hours. But the feedback I've received, the students really seem to enjoy it and benefit from it. So I hope you participate in that. You may have heard about a program that I like to encourage. I find that engineers tend to bury themselves in spreadsheets and books and work and forget about the real reason why we do what we do, which is to have joy and happiness in this life. And so that leads me to talk about what I like to call live to love, love to live, or 4L. And so I spend the first 5 to 8 minutes usually every Thursday lecture, and we talk about a subject that relates to your life, something that's really important. And so I kind of pre-select these topics. If there's a topic, though, that you would really like me to discuss or address in these 4L for You sessions, let me know, and I'll see if we can fit it in somewhere. But this is something that I found you students really seem to enjoy and resonate with. So it's something that I continue to do, and it certainly helps me with my life, so I hope that you enjoy them as well. The final thing I want to talk about before we get into today's lecture is discussing some travel dates that I have to do this semester. Unfortunately, when you begin to develop a research program and you become more well-known and you begin to have success, you start to have lots of demands on you throughout the world to share your research and to perform more research. And so, unfortunately, or I guess maybe I should say fortunately, that's what's happening to me these days. And this semester I have a lot of research obligations that are going to pull me away from Provo for a little bit of time, and is going to require that I give some presentations and help other folks with some research. And so I have a couple of dates listed down here that I know for sure I'll be traveling, and you can see those dates and times. During those times when I'm traveling, I'm going to try to have pre-recorded lectures and make them available to you like this. And what I would prefer that you do on these days where I have these lectures is that you watch these videos before the scheduled lecture time. On your own time, maybe you can make a hot date out of it, or eat some popcorn or cheesy pizza or whatever you want. Watch the video. I'd prefer that you take some notes. You could print out the PDF notes that I prepare for you guys on Learning Suite ahead of time, and you can just fill those in while you watch the lecture like normal, or you can take your own notes however you would like to do it. But certainly taking notes is proven to help you retain material and understand and memorize things better, so I recommend that you do take those notes. The nice thing about these recorded videos is you can go back and watch them as many times as you want. You can skip around to the sections that you really want to see, and so hopefully this will be a benefit and a resource to you. And in fact, I'm kind of using you guys as a guinea pig because I've been leaning this direction a little bit anyways, wanting to pre-record and develop some lectures which will allow my students to watch them on their own time and then spend more of class time answering your specific questions and maybe helping with homework and those kinds of things. So we'll see how this works out. But at least in the case of this semester, when I'm traveling, watch the lecture ahead of time on your own time, and then I encourage you to come to class during the regularly scheduled lecture time. I'm going to have 1 or 2 TAs there, and they'll be there to answer your questions regarding the lecture material, the homework, or whatever else that you guys need help with. I did mention briefly about the notes. If you go to Learning Suite and go to Content, you'll see a content page called Student Lecture Notes. You'll see there every week I'm going to put up PDF copies of the lecture notes I intend to cover. I would like you to please print those out, or just if you have a digital tablet or device like that, get the electronic copies and bring those to class and annotate them while we go through the lecture. They'll help keep you more engaged. They'll help you learn the material better, and hopefully I've really tried to prepare my lectures in a way that the ideas build upon one another and they make sense to make learning more efficient and fun for you. So this is everything I wanted to cover at the beginning of class, and certainly I'm sure questions will arise. Feel free to shoot me an email or send me a text. Now, let's get into today's lecture. It's a little bit more of a review from some of your geology classes and material that may have covered, but we will get into a few new things hopefully, and I think you'll like this material. So what I really like to discuss here at first are the 3 different types of rock. Now, this class doesn't necessarily deal with rock by itself, but I hope you understand that when we talk about soil, all soil comes from rock. It comes from when we weather rock, and rock breaks down, it becomes soil. So if we understand some things about the parent rock, then we can understand a little bit about the soil that results from it. So you may remember that there are 3 types of rocks that we have on the earth. There is the igneous rock, which comes from molten magma. So this is rock that was melted beneath the earth and basically cools and forms rock and crystallizes. We also have sedimentary rocks. So these are rocks that are formed by cementing and compacting different types of soil, and they basically recrystallize into a rock. And then of course we have metamorphic rock, which is rock that is transformed. It can either be igneous or sedimentary, and it's transformed due to intense heat and pressure. And so these are the 3 general types of rocks that we have on the earth today, and all soil comes from these types of rocks. Now, soil itself comes and is formed by the process of what we call weathering. Now, weathering has another name, erosion. though erosion also implies transporting the material away. Weathering is just a process of breaking down the rock and forming smaller sediment. So I want you to pause the video for a minute and think on your own see how many forms of weathering you can think of. When I say mechanical weathering, I'm referring to weathering that occurs due to some sort of physical action on the rock. So pause the video, see how many you can come up with. Okay, so I'm back. Hopefully you had a chance to write down as many of the mechanical weathering as you can come up with on your own, and let's see how many you got right. So right now I've listed 6 forms of mechanical weathering. The first one is due to water. Water is probably the most common form of weathering that we have on the earth today. Related to that is glaciers. So glaciers are frozen water that slide downhill due to gravity, and that grinding action between the rock and the ice produces soil. Wind. Now, you may wonder, how does wind cause erosion? Well, wind causes erosion when it blows smaller particles like projectiles that hit against the rock and then cause it to fracture and eventually wear down. So think of like a sandblasting. That's the same as wind erosion. Thermal expansion and contraction. So this is where if you heat up a material or cool a material, it tends to shrink or to expand, and that shrinking and expanding can eventually cause fractures to build within the material and break it down into smaller particles. Freeze thaw. Now this is similar to thermal expansion and contraction, but it involves the presence of water, because when water freezes, it expands big time. And that expansion can jack the rock apart. So if you get rock that has a lot of fractures and cracks in it, gets water down in those cracks, and that water freezes, it can just blow the rock apart. And finally, gravity or landslide. So this is where if you have fractures in the rock, gravity is always trying to bring the material down. And eventually it can break the rock, and the rock can slide downhill, and then you have smaller and smaller material. And then also the material that's sliding down impacts other rock and material and breaks it down. And so we call this type of material colluvium. So all of those are mechanical weathering. Another process of weathering is called chemical weathering. And chemical weathering is where we start to develop some really, really small particles. This is when we get acids and salts that react with the minerals and break them down to form smaller and smaller minerals like clays and silts. So in general, we say that mechanical weathering is what forms sands and gravels. And these types of soils we generally call coarse-grained, or we call them cohesionless soils. And then the chemical weathering tends to form what we call silts and clays, or these are fine-grained soils. And they often get called cohesive. In other words, they're kind of sticky, though not all of those fine-grained soils do show cohesive properties. So when we talk about in general terms here, and we say soil formations, there's 2 types of general soil formations that develop. The first type we call residual soil. So residual soil is it's like that kid who graduates from college but moves back into his mom's basement and never really leaves and just wants to stay home, never wants to go out and make his own way in the world. That's a residual soil. It's a soil that was formed from a parent rock but doesn't get transported away, it just stays right by its parent rock. And so this is soil that forms in place. Some properties that are associated with this soil, these soils tend to assort themselves with depth according to size. So we get really fine soil up near the surface, and then it gets coarser the deeper we go into the soil profile. The properties of the soil, the chemical properties, like whether it reacts with acid or those kinds of things, they tend to be the same as the properties of the parent rock. And then finally, the soil itself tends to be pretty uniform horizontally. So in other words, if I come in and I dig a boring, say right here, and then I come over 20, 30, 40, 50 feet, and I put another boring down, I'm going to see really similar soils. I'm going to see really similar stratigraphy. That's a telltale sign that you might have a residual soil. And so these are kind of the properties that we want to be aware of. I just want to say that residual soils are relatively rare. And the reason for that is because a lot of the processes that weather rock and form soil also transport the soil away. So more common are transported soils. So these are soils that have been moved away from their place of origin, that have gone out into the world and wanted to make their own way and their own path. So there's 6 different types of transported soils. And they have these geologic names, these geologic terms that we use to describe them. Take a moment, pause the video, and see if you can correctly guess what the different mechanisms of transportation are for each of these 6 descriptions here. Okay, I'm back. So hopefully you had an opportunity to pause the video and to try to guess the different modes of transportation from each of these 6 descriptors. So let's see how many you got right. When we talk about alluvial soil, this is soil that was moved and transported by running water, streams, rivers, those types of things. When we say lacustrine soils, these are soils that were deposited in lakes. So here in Utah, along the Wasatch Front, most of our soils are lacustrine because they were deposited by the Great Salt Lake, which was here thousands and thousands of years ago. Glacial soils, this is a really hard one. These are soils that were, of course, deposited by glaciers. Marine soils, yep, you guessed it, deposited by the ocean, wave action, or deposited within the ocean itself from rivers that come into the ocean. Aeolian, this is a tricky one. Let's see if you got it. This is soil that's deposited by wind action. So dunes, those types of things, those types of formations are formed by the wind. A infamous type of soil that's deposited by wind is called loess. It looks like it's pronounced loess, but it's pronounced loess. This is wind-blown silt. They have a lot of this type of soil up north of us in Idaho, like around Pocatello, and this can be really problematic soil, and you have to deal with it in certain ways. And finally, colluvial soil. So this is soil that is deposited or transported by landslides, rockfalls, gravity movement, those types of things. So let's talk a little bit about particle size. So soil can range anywhere from itty-bitty, teeny-weeny soils that are so small you can't even see it with your eyeball, to soils that are as large as a bus, big boulders, and everything in between. We call all of that soil. And so we can distinguish between different types of soil by looking at the particle size of the individual grains of the soil. So you can see we range from boulders down to cobbles, then smaller gravel, then sand, then silt, and all the way down to clay. We tend to draw a line between sands and silts, and usually what we call the 200 sieve. That when I say the number 200, that's the size of the sieve, and we'll get to talking about sieves in the next lecture. But that is an important dividing line. We say anything that is smaller than that 200 sieve, or I'm sorry, anything that's larger than that 200 sieve, we call it coarse-grained. And anything smaller than that 200 sieve, or that passes through it, we call it fine-grained. Now, there's another way we can distinguish. We can have soils that tend to not demonstrate any type of sticky properties or behavior, and we call those soils cohesionless. And you guys have seen this, right? When you try to make like a sand castle with dry sand, the particles don't stick together, and you just end up with a pile of sand. But if you have a sticky soil like a clay, then it tends to be cohesive and has some sticky properties, and you can mold it and form it and do all sorts of stuff. Now the cohesionless soils, they're bulky, they tend to be dominated and governed by Newtonian forces or gravity forces. So this is like force equals mass times acceleration kind of stuff. The cohesive soils tend to be very small and flaky. And so these small flaky particles tend to be governed more by electrostatic forces, surface forces, those types of forces that aren't necessarily Newtonian, but tend to do more with electrical charges. So let's focus on those really small particles for the rest of the lecture, specifically clay particles. Now, we're not going to get into a lot of clay mineralogy in this particular class, but it is important for you to understand a couple things. First of all, understand that the mineralogy is what governs all of the behavior of a clay. Clays tend to be the most problematic soils, and for the most part, if we had nice dense gravels or sands, geotechnical engineers would be out of a job. But because we have problematic soils like clays, geotechnical engineers are needed to help find solutions so we can build stuff on the soil. So when we say clay mineralogy, what we're referring to is what the clay is composed of on the micro or nano scale, even on the molecular scale. So there are several different types of clay minerals, dozens of them out there, but there are three that are the most prominent. And the other minerals tend to be kind of offshoots of these three minerals. The most common then are kaolinite, aeolite, and montmorillonite. These are the three most common types of clay minerals. Montmorillonite has some other names. It's also known as smectite, and some people call it bentonite. So if you go to Wyoming and hear about a bentonite mine, then that's what they're talking about. Now, even though these are different types of minerals, on the molecular level, all clays are built the same way. They're comprised of two basic building blocks. The first building block is what we call a silica tetrahedron. So this is a molecule that is comprised of 4 oxygen or hydroxyl ions with a silicon ion in the middle. The second building block is what we call an octahedron, usually an aluminum octahedron, though it doesn't necessarily need to be aluminum. It could be any metallic cation like magnesium or sodium, for instance. But these two types of building blocks or molecular building blocks are what build and comprise all clay minerals that we know of. So, we can look at different types of clay minerals, both on the really small scale, like the nanoscale, and we can look at them on the big scale. This is the stuff that you can see with your eyeballs. So kaolinite, if you look at the electromagnetic images here of the electronic microscopic images of the kaolinite, you can see that it's really, really flaky, and the flakes are stacked really closely together. And kaolinite, therefore, is a clay that's not really sticky at all. It's very velvety, very smooth, and it has a lot of useful purposes. For instance, a lot of foods, including some of my favorite, like Chinese food, has a lot of kaolinite additives in it. It's crazy to think that you're just eating clay. But why do we do it? Well, because it's cheap and because it fills you. And so, and because it's inert and harmless. And so a lot of foods have kaolin in it. So anytime you look at ingredients on food and you see kaolin as an ingredient, guess what? You're eating clay. Aeolite is a mineral that also is pretty flaky, as you can see, but the flakes tend to be larger and a little more separated. Now look at montmorillonite. It almost looks like a honeycomb. You don't see individual flakes or particles, but you do see a lot of void space. And that goes to describe a lot of the behavior of the clay mineral. And why is this? Well, because when we look at these flakes, what are causing these flakes to occur? The silica tetrahedra and the metallic octahedra get together in large horizontal sheets, and they form these plates or these sheets that then stack together. So the silica tetrahedra get together, form their sheets. The octahedra get together and form their sheets. And then these sheets start to stack themselves. So for instance, I'm going to go to the whiteboard now for a minute. So imagine now if I draw a box and I represent that box, that box represents, I'm going to call it gibbsite. So this is another name for an aluminum octahedral sheet. And then I use this shape here, this tetrahedron, to represent the silica sheet. So I can start to stack these sheets in different patterns. For instance, I may be able to stack like a silica sheet with a gibbsite sheet and another silica sheet with another silica sheet down here. And it could go on. I could stack them like this. And there's lots of different ways I could stack these sheets. And the other things that will change these sheets are the different types of ions that are in the octahedral sheets. For instance, do I have magnesium? Do I have aluminum in there? Do I have sodium in there? There's all sorts of different ions that could be in those sheets, and it affects the types of shapes that these sheets can form. Now, how these sheets stack together and form is what's going to determine what type of mineral I have. So for instance, if I have the stacking that's shown here on the left, that's the stacking that's consistent with kaolinite. And there's a strong bond between silica sheets and gibbsite sheets. And so because of that strong bonding in between each of the flakes, there's a lot of bonding, and it's really hard for other ions to get in between them. But if, say, there's more silica present than there is gibbsite, then we might see what's shown here in the middle, where we have, now this is an illite mineral. And illite forms when two silicas bond covalently with another type of metallic ion, like potassium. And so if I have potassium in there, it might form this potassium illite. And illite is pretty stable, but these potassium ions can come and go if there's another ion that's available. And so it can make the illite less stable if that's the case. Now, what if I didn't have any of that metallic ions in there, like potassium or sodium? Then it could cause some problems, because the silica sheets don't really want to bond with themselves. They need something else to bond the two sheets together. So they're going to suck in whatever ions they can find, whether it's whether it's water or whatever it is that has a charge that can bond the two silica sheets. And this is the type of behavior we see in montmorillonite. And that's why montmorillonite has all those large voids, because it lets anything in. This is like the frat party at a party school or something, where they just let anyone in the party, and once they come in, it jacks these sheets apart and it causes it to expand, and once the ions leave, then they come back together and it causes it to shrink, and so it's very unstable. and can have a lot of activity, especially in the presence of water. So in general, when we talk about kaolinite, we're talking about a clay that isn't very sticky. It doesn't have a lot of cohesion. It's not very plastic. And if we move to the right to a clay like montmorillonite, then we're talking about a clay that's very sticky and very plastic, very moldable. And so all the clay minerals tend to fall in between the kaolinite and the montmorillonite in terms of behavior. And that leads me to a very important topic called the double layer. The double layer is, what's the best way that I can describe this? You understand the flaky particles now. But understand that on the outside of the flaky particle itself is negatively charged all along the outside. The ends are actually positively charged, but the outside of it is very negative. And so what that's going to do is it's going to want to start attracting all sorts of what types of charges? Yeah, you got it. Positive charges. It's going to want to attract ions and molecules and anything it can find that has a positive charge. And here on the ends, it's going to want to attract anything that has a negative charge. So that may actually be, believe it or not, other types of clay molecules, right? Because on the sides of the clay molecules, they're negatively charged, and on the ends, they're positively charged. So anyway, as the clay molecule starts attracting all of these positive ions, we call the positive ions cations, it starts to develop this giant kind of cloud of ions around the molecules. And this is just like, think of it like a giant cloud of garbage, of just junk that the molecules are attracting, just baggage. And these are all attracting themselves to the clay ions. And one very important element that's coming in here is water. Water is interesting because water looks like this, H2O. Water has the unique property of being what we call a dipole, meaning that half of it is negative and the other half of it is positive. And because of this, if there's water present, it's going to try to attract the positive end of the water into this cloud as well. And so all sorts of water molecules get built into these ions. And the interesting thing is, because the positive side is being attracted to the clay molecules, you have the outside portion of the water that's negative, and it's pointing out, so it's attracting more cations in. And so when you introduce water with clay, it just starts to attract more and more these cations, and you get big bulky clouds surrounding your particles. This cloud is what we call the double layer. I like to think of the double layer like those inflatable sumo suits that you wear and you go and run into each other and try to knock each other down. The meat of the molecule is inside the sumo suit. The sumo suit itself is just like a big buffer that can make it really, really difficult for what's inside to move around and to govern the behavior of the molecule. And that leads me to this picture right here, because what we see here are two different clay molecules surrounded by a double layer. Now the size of the double layer governs the behavior of the clay as a whole. Let me rephrase that. The size of the double layer relative to the clay particle thickness on the inside is what governs the behavior of the clay mineral. So if I have a really thick double layer, but a really thin clay mineral on the inside, you can see that that double layer is really going to govern the behavior of this little clay mineral on the inside. But if I have a relatively thin double layer relative to the thickness of my clay, then the clay molecule, or the clay particle on the inside, is what's going to govern the behavior of the clay. So just so you might be curious, this guy on the left with the huge double layer is montmorillonite, and the guy on the right is kaolinite. And it governs, therefore, the behavior of what gets sucked into the clay and how that clay reacts, especially in the presence of water. So a couple things to point out when you have these clay molecules. Water is going to get directly stuck to the side of the clay molecules, and we call that adsorbed water. And then the double layer, of course, is going to be comprised of anything like water, calcium, magnesium, sodium, potassium, whatever ion it can get that has a charge associated with it. So why do we care? Why do we care about the double layer? Well, let me make this extremely clear and straightforward for you students. The double layer governs all behavior of clays. Not other soils, but clays. And so if we can understand the double layer, and more importantly, if we can learn to engineer the double layer, we can engineer and even change any undesirable behaviors associated with the clay. So a couple of things that are important to understand about the double layer and why we should care about it. For instance, the thickness of the double layer relative to the clay particle size is going to determine how the particles are going to interact with one another. So for instance, if I have a really thick double layer, then this type of thing, where we see the two particles touching like that, isn't going to happen because the double layers are going to try to keep these particles apart. It's going to look more like this, with this guy's double layer and this guy's double layer, and so the double layers repel and push the particles themselves apart. And so if I have that type of interaction, then we have what we call a dispersive soil. A dispersive soil is where the clay particles get spread out and dispersed evenly, and so that no particles are really touching, but what instead is touching are the different double layers from the different particles. A dispersive soil has general properties that, for instance, it tends to settle more slowly in water. The double layer acts more like a parachute. They tend to be more dense and heavier. They tend to have really low permeability. Water has a hard time working its way through these double layers. It tends to get sucked into the double layer, and it can't really work its way through. They also tend to be less compressible, meaning they don't settle quite as much, but they do have substantially weaker shear strength. Now, if I have a thin double layer, like we saw in our top diagram here where I circled, then we have what's called a flocculated soil. So this is a soil that tends to coagulate a little bit. The clay particles tend to be touching and form kind of like a jumble of sticks almost. Because of that, this type of structure, it tends to settle faster in water. It's more open, but because it's more open, it tends to be more compressible and thus settle more when we put a load on it. It has a higher permeability because the water doesn't get trapped in the double layer as easily, and it also has higher shear strength because these particles tend to lock up and interlock themselves a little bit better than they do in the dispersive soil. The double layer is going to govern what we call shrink-swell potential. So shrink-swell potential is important because this is the tendency for soil to shrink when it dries out and swell or grow when water's added to it. Now there's places in the country like Austin, Texas, for instance, or parts of central and western Texas where when it rains, the ground can swell and change elevation like a whole meter because the ground, just the clay itself, is starting to swell. And it can do nasty number on structures and any sort of infrastructure that's built in those soils, because it can jack them, crack them, pull them apart, do all sorts of problems with it. Because I'm recording this isn't going to work very well, but I'd like you guys, when you get the actual file, this PowerPoint file, to click on this link here and go look at an example of shrink swell potential. What happens when we have clay and add water to it versus what happens when we have a more of a silty loam or a sandy loam that doesn't have as much clay in it, and we add water to it. Another problem is erosivity. So this is the potential for fine-grained soils to be attracted to water and then yanked away as the water flows and moves away. And so when we have dispersive soils, they tend to have a high erosivity potential. And this can lead to problems with like failures of dams and such. And so again, here's another video link. Have a look at it and see for yourself why this is important. If you get some time, also search on the internet and look up, for instance, like the Teton Dam failure, and understand and know that this was caused due to piping or to this erosion of fine-grained material due to water, because they didn't really design that dam very well. Geoenvironmental engineers are masters of the double layer, and they use clays to benefit man and to engineer it such that it performs some sort of intended purpose. For instance, like landfill liners, or converting, say, a body of salt water to a body of fresh water. Those types of things. And so if you have interest and eventually go into, say, environmental or geoenvironmental engineering, you're going to eventually learn a whole lot about the double layer and learn how to engineer it and manipulate it. We won't say too much about that, but when we do get into advanced soil mechanics in the 600 level classes, we'll talk a little bit more about those things. Another application that I think is pretty interesting is in transportation and materials, where, say, we have soil like this that I'm circling here that can be, say, like a very dispersive clay, like a montmorillonite. You can imagine if water gets in there and you have pavement on top of it, it could crack the pavement and do all sorts of problems with it. So if we can change that clay mineralogy from a very active clay like montmorillonite to a less active clay like a kaolinite or even an illite, then it's going to cause our pavement to perform better. So one thing that engineers do, for instance, is we add lime treatment to a lot of these types of dispersive soils, and it will change the properties of the mineralogy of the clay. It causes a swap or a transformation of the metallic ions that are in the octahedral sheets, and literally changes the mineralogy of the clay. And so you may have seen this. We do this sometimes here in Utah, but it's a lot more common in other parts of the country where we want to stabilize these active soils for the purpose of pavement design. If you take a pavement design class from Dr. Guthrie, he'll talk a lot more about this. So I think that's everything. That's the end of this presentation. Thank you for watching this video, and please, again, go to class. If you have any questions, feel free to let me know. Also, hopefully the TAs will be there that day to answer your questions there. And I'm going to post a lecture for Thursday that you can watch on your own free time as well, just like this lecture. So thanks. I'm happy to have you in my class, and I'll look forward to seeing you guys in person next week. Take care.